Let's record. So I know you guys are like confident, or you think that theory can be done easily. Like even I feel like you guys can do it. It's more information. Just read it from the book, mil jayega. But I'll just quickly take it in bullet points. So first of all, why periodic classification of elements? Like why does the table exist in the first place, and why do you have to study it? Any ideas?
Ma'am, because certain elements can have similar properties, and if we know a certain group of elements which have similar properties, we can use them in a better way.
Yes, better way, absolutely. It makes life better, simpler, easier. But how does it make life easier that way?
Classify them like metals, non-metals, metalloids, or on purpose, like they are halogens, noble gases.
Absolutely. So classification makes studying easier. It's a combination of what Puneet said and what Elena said. So you're classifying them, and as Elena said, you're classifying them based on the similar properties. So if you come across any new element, you can predict uska properties kaise rahega. So after like 3 years, if someone discovers some element with like one electron in the valence shell, you can be like, oh, ye to sodium, potassium unke group mein aa raha hai. So you can fairly figure out ki okay, iska hydroxide kaise rahega, oxide kaise rahega. So classification makes studying the existing elements and new elements easier. Is the same reason bio में भी बहुत सारा classification होता है. You classify as mammals, birds, reptiles, and then diversity chapter था ना? You guys study last year, or was it deleted? It was deleted. Okay.
It was deleted.
Deleted.
Okay. So that chapter was all about classifying living things. Here we are classifying your chemicals, elements. Okay. So now that we got out of the way, obviously, like initially when people discovered elements, they could study it individually only. There were not like so many of them. But slowly, as more and more elements kept getting discovered, it was getting difficult to study each of them individually. So there have been a few attempts at starting this classification. Okay. Sabse pehle, like the first effort at classification came from this German scientist, German guy. He's also an inventor, Dobereiner. Okay, what did Dobereiner say? How did he classify elements? What was his thing?
Triads.
Law of triads.
Absolutely, very good. And what is the law of triads?
Like when an element that consists of when three elements are arranged in order of their increasing atomic masses, then the atomic...
One moment, Puneet. So any three random elements, or...
No, which have similar properties.
Correct. Three elements with similar properties. Yes, continue.
Are arranged in order of their increasing atomic masses, then the atomic mass of the middle element will be roughly equal to the average of the atomic masses of the other two elements.
Absolutely. That is what Dobereiner found out. So when he started grouping similar elements together, and he arranged them in an order that makes sense, increasing atomic mass. This is quite important, atomic mass. So throughout history, we'll be dealing with atomic mass only, because concept of atomic number was not discovered until 1930, like sometime during the early 1900s. Okay, so till then, we'll be working with atomic mass only. So arranged in increasing order of atomic mass, then the mass of the second element is roughly equal to the average of the first and third, like other elements. Okay. So this pattern was followed with quite a few elements that were known during that time. So famous examples, so you have lithium, sodium, potassium. the halogen family. You get this also with fluorine, chlorine, bromine. Yeah. More examples? Any of you guys can mention? Fluorine, chlorine, bromine, like chlorine, bromine, iodine. Chlorine is little. Okay.
Was there around calcium,
Calcium, yes.
magnesium, and no, sorry, sodium and Ba something was there. I don't know what is Ba.
So calcium, strontium, barium. So Ba is barium. So this is strontium. Strontium. And Ba is barium. Okay. So barium sulfate, you guys have worked with barium before. Strontium is the new one that we haven't come across earlier. So in each of these cases, test it out. You can absolutely do it. So I'll give you an example. Let's do a problem here. The kind of questions you'll be asked is, you may be asked about the statement, you may be asked for examples, or you may be asked an application based on this. So for example, if I know that chlorine ka atomic mass is approximately 35.5 and iodine was found out to be approximately 127. So what is the atomic mass of bromine? Can you find out?
Add them up and divide by 2.
Yes, find the average of the other two. Send the result you get over chat. Then we'll check if, like, does this fit or not, whether it's right or not. No, Elena and Mansi have sent and both got like very, very different answers. Yes, check kar lo calculation. Are you adding correctly? Are you dividing correctly? Divya, we're talking about atomic mass. तो इतना कम कैसे हो सकता है? 24 is not the answer. Check again, Divya.
So, ma'am, it is 12.7 or 127.
127. Iodine like बहुत ही बड़ा है, like it comes right at the
Oh,
bottom.
I took it 12.7.
No. Okay, Dhruv and Mansi got it. Puneet also got it. Puneet, you've rounded it off. Okay. Nice. Chalega, that's fine. Approximately equal hona chahiye. So that's completely acceptable. So you guys got these values, no? Anirban, have you done it?
No.
Neki, average find out karna hai, not the sum. Anirban, where are you stuck? What happened? Are you still calculating or are you stuck somewhere?
Calculating.
Calculating, ठीक है, कर लो जल्दी. Okay. So middle element ka atomic mass, he found out that it was approximately kind of the average of your first and third thing. So in दोनों का average find out करना है. Average is basically add them up plus 127 and divided by 2. इनकी दो है. So all of you got 81.25. Now when we check in reality, what is the atomic mass of the middle element, bromine? 80. So generally it's supposed to be 80, and you guys got almost like 81. So approximately equal here. So even if you get a question saying verify Dobrainer's law of triads, this is what you do. You take an example, you show that these elements have similar properties, like सबका valency है यहाँ पे -1, यहाँ पे सबका valency is +1. So they have similar physical chemical properties, and then you take their atomic mass, show this calculation, and be like, look, it is equal to the average of the other two elements. So that proves the law of triads. Now, but
Ma'am,
unfortunately,
for that, we have to know the
Ma'am.
masses of all the elements, right? For bromine, then we have to know it is 79.
so learn, like, pick something that you're familiar with. I would say go with this because you've worked with these elements frequently. Like lithium is
No,
7.
matlab we can choose the triad or they will give an exam.
Only 3 triads are there in total.
And it depends. If they just say verify the law of triads, you can do it. But if they specify verify the law of triads, whether it applies for the set of elements, then you have to like do it for those elements. Okay, so it completely depends on what is asked. Okay, but unfortunately, Dobriner was alive during 1800s. So when Dobriner came up with the law of triads, there were only like 30 something elements that were known. Like all the elements existed, but only 33 or some elements were discovered. So
33.
so within those 33 itself, like Dobriner could identify only a limited, like 3 or 4, just these many triads. He could figure it out. It fit only with these many elements. And when he started applying it to other elements, it just did not fit. Like iron, cobalt, nickel, they showed similar properties. Like for example, copper shows valency of +2. It's a metal, just like calcium, magnesium, all of that. But it didn't fit in with the law of triads. Like there was no relation. The way average fit neatly with these elements, that way Inca atomic masses just didn't fit in such triads. Okay. Okay. There was an attempt, but that attempt failed. So next comes Newlin's law of octaves. So some time passes. This was in 1860 something, I think. So Newlin's law of octaves. John Newlin was a scientist. He was a British scientist. Dobriner was German. He also attempted a classification. Now, what Newlin did is instead of picking similarities, he just took all of the elements that were known during his time and he arranged them in increasing order of their atomic masses. Okay, so now what did Newlin find out? What was his contribution in classification? Any of you guys remember? Dhruv, Nikki, Elena, any of you guys?
Every eighth element, like octave, means eighth. So every eighth element has similar properties, just like the notes, musical notes.
Correct. Any of you guys are into music? Like, did you learn music or classical?
Yes, ma'am, I did.
Western, whichever. Oh, you did? Okay. So which are the musical notes?
If we talk in English or that side, then it is do, re, mi, fa. Or the normal Hindi notes are also sa, re, ga, ma. But then it again ends with sa, right? So the first and last name is basically C, which is same.
Yes. So it's there. Your notes are sa, re, ga, ma, pa, the, ni. And then sir, it sounds the same as the first sir. It's just a different octave. Like it's like a higher pitch sir, right? And then if you count, it's 1, 2, 3, 4, 5, 6, 7. Every eighth note repeats back again, right? So Newland observed that the exact same thing happened with chemical elements also. So he started arranging starting with hydrogen. Tabhi noble gases were not discovered yet. So hydrogen ke baad lithium, beryllium, boron, carbon, nitrogen, oxygen. And then eighth element, the eighth note repeated back again. And then he observed that if you look at it, so hydrogen exists as H2 gas, fluorine exists as F2 gas, chlorine exists as Cl2 gas. All of them show a valency 1. Again, lithium, sodium, potassium, copper, like all of these show very similar properties, valency +1, plus they're all metals. Same thing kept occurring in every single group. So this is what Newlin's law of octaves said. So he went one step further, saying physical chemical properties are repeating at every eighth element, just like how musical notes are repeating. So that is Newlin's law of octaves. Okay. But again, Newland also faced a problem because one, he also had to work with very limited number of elements. A lot of elements were not discovered, which meant that, you know, some of them fit, some of them didn't fit. Like this is applicable up to calcium only. Beyond calcium, if you go, if you look at it, hydrogen, fluorine, chlorine, all are non-metals. But suddenly cobalt aa gaya, which is a metal. Again, completely different properties there. So as the mass kept increasing, it just didn't work out well, which is why it worked to some extent, but eventually that's also not like the ultimate way of classification. There was no pattern there. Okay. Next, the next attempt was Mendeleev's periodic table. Mendeleev was a Russian scientist. He was a chemistry teacher, and his was the first ever step at coming across, like the only reason why we don't use Mendeleev's periodic table, the sole reason is that his was based on atomic masses, which is why some of the places it doesn't fit very well. Now we have come to know that even more fundamental property is the atomic number, which is why we use the modern periodic table. But Mendeleev's, like, he's the father of the periodic table. The modern periodic table ka design definitely comes from Mendeleev's table only. So his is like a first serious proper attempt. His work for a lot of years. Okay. Mendeleev's periodic table, what Mendeleev did is he actually shut himself in his room, like in the university, for like 2-3 days, and he didn't go like Dobriner, where he just picked the elements with similar properties. He didn't go with Newland, where he was just blindly arranging them in increasing order. Mendeleev took each and every element, like he made like kind of cards out of each and every element, and then he started arranging them one by one to see, you know, to make sense of it basically. And he did this for like 2-3 days. At the end of, you know, 2-3 days, he was basically like shut out from the rest of the world. Like he was just in his room working on this. So at the end of it, what we get is this table, like Mendeleev's periodic table. So just looking at this table, you can kind of make sense of it. So for example, he went purely by the similarity in properties. So he said, किस तरह का oxide बनेगा, किस तरह का hydrides बन रहा है, this particular property. So all the elements that make oxides in the form of RO, like so this should be R2O either. Yeah, like H2O, Li2O, Na2O. And then he put all the elements that make oxides in the form of RO, like magnesium oxide, calcium oxide, strontium oxide. So that way he went purely on the basis of physical chemical properties, and within that he arranged them in increasing order of the atomic masses. Okay. So let's say hydrogen, lithium, sodium, potassium, all these made the same type of oxide, same type of hydride. Within this, he arranged all of them in the, like, instead of putting it randomly, he started off with smallest one and then slowly increasing order of atomic numbers he arranged it. Okay. And then he recognized the differences within certain types of elements. Like you can see within group 1 itself, he placed potassium and copper also. So he observed that potassium, copper, both of them form like K2O and Cu2O, cuprous oxide. But he also had the sense to notice that copper was slightly different from potassium and sodium. Like copper was not as violently reactive like sodium, potassium, rubidium. Copper also showed variable valency. It formed Cu also. It formed Cu2 also, which is why within each group he made subgroups like 1A, 1B, 2A, 2B. So his was the most systematic form of classification. Okay. And because he made space for all of the differences and then he made it like extremely systematic, Mendeleev's periodic table was the most useful of all. And yeah, that's why he's considered the father of the periodic table. Okay, so we'll look at what all are the contributions of Mendeleev's table. So Mendeleev's periodic law, like his main thing, like the backbone of his classification is that the properties, like physical and chemical properties of elements, are a periodic function of their atomic mass. So he borrowed slightly from Newlin's idea there, but he took it further. So he said periodic function matlab repeat hone wala. Like you have time period waves oscillations mein. So at every 7th element or every 8th element, the periodic like the physical and chemical properties keep repeating. You find similar physical and chemical properties. Okay, so that was his law. First, he said elements were arranged on the basis of their atomic mass and similarity of chemical properties. So that was the main thing. Then he examined the relationship between atomic mass and its physical and chemical properties. This was the periodic function I was talking about. In order to study the elements' chemical properties, he examined their compounds formed with oxygen and hydrogen. And he specifically chose this because they are the most common types of compounds that all elements form. Metal ho ya non-metal, you always find its oxide, you always find its hydroxide, you always find its hydride. So that is what he checked, like oxides or hydrides. Type of oxide, type of hydride. When elements were arranged in the increasing order of their atomic masses, there was a periodic occurrence in similar physical and chemical properties. So from point 4, point 5 is the important bit. The properties are periodic function of their atomic masses. So this statement is important. This is called Mendeleev's periodic law. Okay. Mendeleev's periodic table consists of horizontal rows called periods and vertical columns called groups. So this is also pretty intuitive. Vertical columns called group because like you group similar things together, right? So vertical columns may you have all the similar elements, so they are called groups. Horizontal rows are called periods because like you go through one row and then the next row there is like the properties repeating again. So that's the idea behind why are these called groups and why are these called periods.
Ma'am, in the table, in the 8th group, were there 3 elements in the 8th one?
Nice, very good question. So all of these elements formed oxides in the form of like RO4, and they had they're very, very similar in their physical and chemical properties. So there is a marked difference between sodium and magnesium. Like, yeah, both of them are metals, but in terms of their reactivity, in terms of their appearance, there is a lot of difference, right? But the difference is not so like as much between iron, cobalt, nickel. So they're very, very similar, which is why he put all of them like together. They're kind of like a triad, groups of three. Okay.
Okay.
Yeah. Okay. So before we get to achievements, like how did Mendeleev's periodic table help? Like, why is it such a landmark moment? Is everyone clear about how did Mendeleev make the table? What was his periodic law and the funda behind it? So if there's any part that you don't understand or any question that occurs, definitely ask. Okay. Anirban, Dhruv, Neki, Aditya?
No doubt.
No doubt. Divya? Okay. Okay. Then
No doubt.
cool. Achievements of periodic table, basically advantages or what is so special about Mendeleev's table. This is like the main thing. So Mendeleev could predict the properties of elements that were not discovered at that time. So this was like a really great thing at that point of time, because whoever had worked on this before Mendeleev, Dobriner, Newland especially, he didn't give that space for, like for that possibility that maybe we don't know some of the elements that existed. But Mendeleev, because he had a one-track mind. All of these need to be categorized and classified so that it's easier to study. So he did not stick to his rule that increasing atomic mass matlab वैसे ही होना चाहिए. Like, he did not stick to that. He gave priority to the fact that the elements needed to have similar elements needed to be grouped together. Okay, so I'll actually show you what his actual periodic table was. This is like a adapted to modern time type thing that is displayed here. I'll show you the original periodic table that Mendeleev had made.
His total elements were 63, na?
Yeah. So when Dobriner started, it was like 33. When Mendeleev started, it's like 60 something. Yeah. Oh, this is so small. This is a good one. Okay. Is it visible or is it like small for you guys? How does it look like?
Visible.
Visible clearly? Okay. So concept is the same, design is different, but you can see the concept is the same. You still have groups. Properties, like he considered hydrides, he considered oxides. Again, because it's a different country, it was a different time in history. Instead of subscript, it is written in superscript here, but the idea is the same. And you can see that, you have group 1, group 2, group 3, group 4. It's arranged exactly like this only. Yahan pe you have like sets of elements. You can see like yahan pe there is no element here, but he kind of predicted that yahan pe kuch to hona chahiye jiska atomic number it is somehow close to 44. So calcium ke baad he didn't simply put titanium here, like because he didn't find that titanium was similar to rest of the elements in this group. Titanium fits better here. Like titanium forms titanium dioxide, TiO2. which is similar to your carbon dioxide, silicon oxide, silica, SiO2 and all of that, right? So he figured that यहाँ पे एक blank space छोड़ना चाहिए because titanium shows more similarity with this group 4 than group 3. So that was like a foresight that Mendeleev had. And because he went with the pattern that sare, like the properties are repeating, he could figure out the pattern कि increase हो रहा है तो कैसा increase हो रहा है, decrease हो रहा है तो how is it decreasing. So based on that, he predicted the existence of elements that people did not know of. So that was like a landmark thing that Mendeleev did. Okay. So which were those elements? Like gallium he predicted, scandium he predicted. So which were these elements?
Germanium.
Germanium is another one that he predicted. So gallium, like discover होने के बाद people called it gallium, but Mendeleev called it eka aluminium. So kind of like, like to mention that it is similar to aluminium, but it's not aluminium. It's like aluminium versus aluminium version 2.0, that sort of a thing. That's what like the prefix eka was like. So he called eka boron, eka aluminium, eka silicon. So you have gallium, germanium and scandium that way. Okay. So that was like a major achievement of Mendeleev. He could predict the properties of elements that were not discovered yet. The next one is noble gases were discovered much later because they were inert, they didn't form any compounds. So unless somebody could simply figure out from air ki kya gases hai in the air around us, people didn't know of noble gases. So even though they were not discovered during Mendeleev's time, his was organized enough and gave, like, because he prioritized similar physical and chemical properties, noble gases ka you could simply add another column on the right side here and add all the noble gases in the end. It did not disturb the rest of the table. Discovery of new elements basically did not disturb the rest of the table. Yeah, so that's like advantages, achievements of Mendeleev's table. But again, because we didn't know enough about chemistry during his time, there were some drawbacks to it. So first drawback, position of hydrogen. Like hydrogen was already discovered, but where to place hydrogen in the periodic table has always been a problem. It is still a problem. Why is it still a problem? Lies in what hydrogen is. It's basically issue with the properties of hydrogen itself. Okay, so why is it an issue? What all do you know of hydrogen?
It does not have any neutron, one proton and one electron. So to achieve the to become a noble gas, it could either give its electron or take its gain electron. So it could act as an alkali metal or a halogen.
Correct. So it can either lose electron showing valency of +1 or gain electron showing valency of -1. So this is like similarity with metals, similarity with non-metals. Okay. So where should you place hydrogen? Should you place it along with metals with like sodium, potassium and all, or should you place it with halogens like fluorine, chlorine that show -1 valency? That's an issue with hydrogen. Not just this, but hydrogen also exists as H2 gas, which is similar to Cl2, F2, Br2, similar to non-metals. But if you look at the electronic configuration of hydrogen, it has one electron in the valence shell, which is similar to lithium, which is 2,1, sodium, which is 281, potassium, which is 2881. Here. So what principle should you use? So should you place hydrogen with sodium, potassium, like इनके group में डालना चाहिए कि इनके group में डालना चाहिए? So that is the problem with hydrogen. So the same problem has continued even now with in the modern periodic table. That's a debate that has never been settled. Next. Now Mendeleev took his fundamental property like increasing order matlab, he took it to be atomic mass. But isotopes exist. So isotopes matlab atoms of the same element having different atomic masses. So you have, like if you take carbon, you have C12 also, C14 also. So how do you handle it? Like, should you place carbon normally, or should you place C12 separately and uske baad C14 separately in two different groups? Like, if someone asked a question ki, if there are different atomic masses, why did you take only a single, like why did you take carbon 12 and place it there? Mendeleev basically did not have an answer beyond, again, similar properties, uske basis pe jana padega. And the third drawback is, in certain pairs of elements, the increasing order of atomic masses was not obeyed. So as a general rule, Mendeleev said that you need to arrange it in increasing order. But if you start nitpicking, Mendeleev himself did not follow that order. Like you can see aluminium 29.98, silicon 28.09. Again, that could be an issue with isotopes and all. So there are certain places where Mendeleev himself did not follow that increasing order of the atomic number wala atomic mass wala rule. Again, that is because he prioritized similarity in the properties more than these other things. Okay. And fourth, next drawback is the masses of the elements did not increasing in a regular manner. Like in some places it would increase like 1 ke baad 7 aa gaya, like hydrogen ke baad lithium, and then beryllium was 8, uske baad it'll skip to 10. Like it's not a regular increase when it came to the heavier elements. So you couldn't exactly predict, okay, like if there is a large amount of difference, is there like one unknown element, like zinc ke baad gallium germanium aana chahiye ki, are there more than these two, or how many unknown elements are there? Like that regularity was not there, which all of these things except for position of hydrogen, it was purely because lack of knowledge during Mendeleev's time. He was working with atomic masses. That is the reason modern periodic table, this is what we use right now, because this took atomic number as the base. Yeah, Dhruv, Divya, what's up?
Ma'am, can you again just tell the demerits of Mendeleev's periodic table?
Demerits, these 4 points is, no? Like first is position of hydrogen, because hydrogen behaved like a metal, like with one valence electron, but it had similarities with non-metals also, being H2 gas, forming covalent bonds. So it was a debate whether to keep hydrogen with metals or with halogens. Others are related to atomic mass only. So one point being isotopes. Do you guys remember what isotopes are? We studied that in grade 9.
Same number of protons, different number of neutrons.
हाँ, तो उसकी वजह से क्या होगा? Like, what if there are different number of neutrons?
Atomic
mass will change.
Correct.
But the properties will remain the same.
Exactly. So, because Mendeleev's table was based on atomic mass, just a second. Nikki, that's fine. Like I was just checking the similar, like hydrogen ke properties only. I put it on the whiteboard and I'll check it. I'll show it later. Okay. Now I'm just discussing demerits again. Okay. Yeah. Speaking of isotopes, different atomic masses. Now Mendeleev's whole table is based on atomic mass only. So if you had the same element with 2 atomic masses, how will you handle that? like carbon 12 है, carbon 14 भी है. So will you place carbon twice, or should you place it like before nitrogen, after nitrogen? So that doubt will come up, right? So that was another drawback or a question that Mendeleev had to answer. The third problem, Mendeleev did not follow his own rules in some places. Like he said, table mein you need to arrange it in increasing order of atomic mass, but there are some places where he did not follow that. Like if something had a bigger mass, it was still placed before an element with smaller mass. Like that increasing order did not happen in like 2-3 places in the
I
table.
mean, cobalt and nickel.
Cobalt nickel is one, yes, very good catch. So Mendeleev का आंसर था कि yeah, increasing order, but more importance was given to the similarity in properties more than the other thing. ठीक है. And fourth drawback is it did not increase in a regular manner. Regular manner in the sense it wasn't like 7 के बाद 9 के बाद 11, like it was not exactly 1-to-1. Like you couldn't put an equation to it to figure out कि atomic mass 10 के बाद क्या आएगा. Is it going to be 11? Is it going to be 12? Like no one knows. So that order nobody could find out कि like whatever existed they put it in increasing order. Beyond this, okay, platinum का okay, bismuth is 208. इसके बाद क्या आने वाला है? Is it 210, 211? So that they couldn't figure out. Another problem was if there was undiscovered elements, people could figure out, okay, like suppose 200 people knew, uske baad 208 hai. So people didn't know 200 or 208 ke beech mein how many unknown elements are there. Is it just 2, or is it like it could be 3 also? 202, 204, 206 bhi ho sakta hai. So that pattern like Mendeleev couldn't figure out. Like it did not increase in a regular manner when it came to heavier elements. So he could not predict how many elements were unknown between any two elements. Okay, so these are like the drawbacks of Mendeleev's table. So except for the position of hydrogen, all of these get sorted in the modern periodic table purely because this uses atomic number instead of atomic mass. Okay. So now we'll get to the meat of the chapter, the actual periodic table. So before we start, how are you guys feeling? Like, should we continue or do you want to take like a 2-3 minute break? How is it going?
It's a 2-3 minute break.
2-3 minutes break.
Okay. So 3:51 हो रहा है ना? So we'll resume at 3:55. So if you want, you can revise up, take a deep breath, go have 3:55 ko we'll come back. So modern periodic table was created by the scientist called Henry Moseley. Okay. And he had created after the discovery of the structure of the atom. So if you remember structure of atom, it didn't happen in one time itself. Like pehle people knew that there were some charged particles, but no one knew how those charges existed. The plum pudding model tha, all of that happened. And then you know, like slowly Rutherford did experiments. The first particle to be discovered was electron. Electron के बाद proton discovered हुआ. Then बाद में neutron was discovered. And then charge of the electron, charge of the proton, masses of them, and how they are arranged in the atom itself. Everything was like basically step by step it happened. Even electronic configuration, how the electrons are arranged in the atom also, like it couldn't happen in one shot. Okay. So after all of that happened, like this was modern periodic table was somewhere around 1932, something like that. So mostly what he found out was he correlated, like he's the one who connected or worked with the concept of atomic number. So he was doing some spectroscopic studies, like playing around with each of these elements, studying them, like what sort of spectrum, like splitting of light, how they are affecting light and all of that. He was playing around with it. So he found out that each element, the X-ray like spectrum, like there was a property of the element which correlated directly with the atomic number. Okay, so that is why we say atomic number is the more fundamental property. It is the most fundamental property of an element. Theoretically also you can understand why it is the most fundamental property. Clear? What is atomic number?
Number of protons.
Atomic number equal to number of protons, correct. And what is the number of protons also equal to?
Number of electrons.
Always in a neutral atom, number of protons is equal to the number of electrons. It is equal, right? And based on the number of electrons, what is decided of an atom?
Valency.
There you go. So depending on the number of electrons, agar 6 electrons hai, to they are arranged in a certain way. So from the number of electrons, you get the electronic configuration. And from the electronic configuration, valence shell mein, do I have 1 electron, 7 electrons, 5 electrons? Depending on that, the valency, meaning indirectly the chemical and physical properties are all decided. Okay. And all of this you can see it is coming from, so valency is decided by the electronic configuration, which is decided by the number of electrons. And how do you know the number of electrons? It should be equal to the number of protons, which is basically your atomic number. So your atomic number is the one that's basically controlling or deciding all of your element ka physical and chemical properties. So purely on the basis of atomic number only, it is decided, like that fate of that particular element is decided. Ki metal hoga ya non-metal hoga ya metalloid hoga. Is it going to be very reactive or unreactive? All of that, its whole thing is decided completely by the atomic number. And why atomic number? What is the relation? Is basically all of this. So number of protons ka equal number of electrons hona chahiye, which in turn gives rise to the electronic configuration. So that's the arrangement of electrons. And based on how many electrons are there in the valence shell after arranging, that decides ki iska chemical or physical properties kya rahega element ka. Okay. So clear about what is the connection, like why is atomic number the most fundamental property? Yeah. Yes, no. Do you wanna switch on your video? At least I can see your expressions. If you're following, not kya ho raha hai. See, if this is not clear, you should like immediately let me know, then I can find a better way to explain. But give some sort of a response, no?
Got it, ma'am.
Correct. Okay. Anirban, Dhruv.
Understood, ma'am.
Okay.
Got
See, if this is boring, if this is something that you already know, that also let me know. Then we can be a little faster. We can focus more on the things that you want to study. It's not a compulsion. Okay. So atomic number is the fundamental property of an element. So let's do the whole table. Let's follow whatever Mendeleev did, but this time we'll use atomic number instead. Okay. And the result from this is what we have as the modern periodic table. So this is a modern periodic table. This is what it looks like. You guys must be familiar with this. You must have seen it a lot of places. Again, it's like a regular table only, like you have horizontal rows, multiple columns. And just like with Mendeleev, you arranged all the elements as per the similarity in their in their physical and chemical properties. The only difference is that you followed increasing order of their atomic mass. So that way you avoided, like you removed all of these disadvantages that has to do with isotopes and irregular this thing and all of that. Atomic number is pretty straightforward. 1 proton hydrogen, 2 protons helium, 3 protons lithium, atomic number 4 beryllium. So it just went on 5, 6, 7, 8, 9, 10 in the same order, regular increase. Okay. The basics are the same. You have the horizontal rows are called periods. So each of these is a period. And vertical columns, each of this is a group. Okay. So if you want to remember it easily, how many of you are fans of Harry Potter? No one? Oh, Neki and Puneet. Mansi has read it. Okay. Just 3 of you. But you must have heard of the movies at least, right? Anirban, Elena, Dhruv, Divya.
Yes, ma'am, I've heard of it.
Okay, heard of it. Okay. So just remember Harry Potter, very good. Horizontal periods, vertical groups. So instead of Harry Potter, if you want to replace HP with something that you like, I don't know, Hercule Potter or anything else that you're familiar with, you can replace it. But just remember HPBG, Harry Potter, very good. And Ajayra. Yeah, Neki? Okay. So horizontal are periods and vertical groups. HPVG. Okay, so don't mix it up. Hydrogen and helium horizontal row make up a period. So this is the second period. This is the third period. Similarly, this is the first group. Beryllium, magnesium, calcium, all this is the second group. This is the third group, fourth group, fifth group, and it goes on. Okay.
So there are 9 periods, na?
7, I think. 1, 2, 3, 4, 5, 6, 7. Oh, so these two it is placed outside of the table, no? So this is one way of representing it. Another way of representing it is called the expanded form. I'll tell you what these two stand for. This is not like an extension of the table. This is not 9th and 8th and 9th rows. There are only 7 periods and there are 18 groups. Okay. 7 periods and 18 groups. 7 horizontal rows and 18 vertical columns. So this is what the modern periodic table is known as. This whole table, again, this whole chapter is about classifying, right? So there are different levels of classification. Okay. So first level of classification, you split it into 4 blocks. So you have the S block, which is just these two groups. And then you have the P block, which is the extreme right side, this whole highlighted region. Then you have the D block, which is the center part of it. And then you have the F block, which is like floating outside the table. The 4 blocks, you have S, P, D, and F. So why are they called SPDF is all related to the electronic configuration. We didn't go to that deep of a level yet, but whoever is going to take chemistry in 11th standard, it will be more clear. Like that's where we're going to study about SPDF. Okay, so just a brief introduction about all of these blocks. S block is extreme left side. All of these consist of metals, and they are mainly very highly reactive metals, explosive metals like sodium, potassium, all of these. P block contains. Yeah, Nikki, what's up?
The 2 lines which are written outside the table, lanthanides and actinides.
Yeah.
For the entire straight line, they have put 1 box in the table.
In the sense, I didn't get you.
Can
Entire.
you display the whole table?
Okay.
So in the third group, the last 2, LA and AC, those represent the entire lines.
This doesn't represent. It is. I'm coming 1 block at a time, right? So I'll explain a little better when I discuss about the F block.
Okay, ma'am.
Yeah. S block, extreme left side, contains of highly reactive metals. P block, you can see oxygen, nitrogen. You can also see that you have, indium, tellurium, you're not familiar with, but you have gallium, germanium, tin, lead. So this contains both metals, metalloids, and non-metals. Okay. So P block contains all types of elements. S block is only metals. D block, this contains only metals, just like S block, but these are not very reactive metals. They are like very moderate. You have your iron, copper, any metal that is not very reactive, something that you work with, you will find it in the D block. So chromium is here, silver, gold. Yeah, there you go. Silver, gold, tungsten that you use in the bulbs. So all of those come in D block. So D block is also called, so these elements of D block are also called transition elements. Have you guys heard of this name before, transition elements, in any other context, any other place? Yeah? Yes? No?
No.
Okay. So they're called transition elements because, or transition metals, because this is where, like you have to go through these elements in order to get to the non-metals, because extreme right, you have proper reactive metallic compounds. Extreme left. Extreme right, you have all the non-metals. So
metalloids.
Metalloids are, again, like you will find metalloids over here. So these are your metalloids. Antimony is a metalloid, yeah. So you have boron, silicon, arsenic, So these are your metalloids, beach mein. So because you have to go through the D block to get to your P block and like non-metal, so these are called transition elements. Okay, this is kind of like a bridge between extremely metallic things and like the elements that show kind of like a non-metallic nature. Beach mein. Mansi tellurium polonium. Huh, beach mein. Polonium is a metal, it's a radioactive metal, but I think tellurium is a metalloid.
This polonium is also metalloid.
Metalloid, yeah.
80, I think 80 is also no.
80 is astatine. That's a it's a radioactive, like yahan se polonium, yahan se like kind of radioactivity kind of starts off. So CN may it's given, okay, it'll be counted, yeah. Yeah, but yeah, it's basically between metals and non-metals you find metalloids. So D block called transition elements. It's like a bridge. And then F block. F block is pretty special. So these two rows, so these are called lanthanides. And these are called actinides. Some of the older spelling, it's a time difference, British versus American wala thing. You may also see them referred as lanthanoids. Lanthanoids and actinoids, whatever, either or. Okay. So the reason is this first row of elements follow this particular element. So atomic number 57. So this is lanthanum. Symbol is La. So all of these show extreme similarity with lanthanum. It is so similar that it's very, very difficult to separate them out or differentiate between them in the way they react, melting point, boiling point. A lot of their properties are very, very similar. That is why
lanthanum is radioactive.
This is not radioactive, no.
But uranium is.
Uranium is. So niche actinoids.
Yeah, sorry, yeah.
So these are called actinides because they follow actinium. Yeah, lanthanum ke followers are lanthanoids. Actinium ke followers are actinoids. Okay. So as simple as that. And again, all of these elements show like similarity with actinium. So actinium is not very radioactivity. Like proper radioactivity starts. All of these are radioactive, but
Thorium
is yeah, all of these are like the last row, all of these are radioactive. Francium, radium, yeah, actinium is also radioactive. The degree, like how radioactive they are, like how quickly they break apart, like that basically differs from element to element, but all of these are radioactive only. Yeah. Okay. So all these elements like thorium, uranium, neptunium, plutonium, all of these show extreme similarity with actinium. So they are called actinides. So they are not separate from the periodic table. They fit within these 7 periods, 18 groups itself. In fact, another way of representing the periodic table. Now this, like usually this is how periodic table is represented to save space. But otherwise, another way of representing it, you have a wider form. So ideally, this is how you would represent the periodic table. If you were to include this within the periodic table itself, this is what it'll look like. You have group 1, group 2. So this whole thing is like following lanthanides. And then you have like group 3, group 4, group 5, and D block, and then P block. Okay. So F block is kind of like within the D block itself. It's a separate group of elements following lanthanum and actinium.
Miss, what is our temperature bar above?
Oh, this is to, this is the key for this particular table. At 0 degrees Celsius, you can see that carbon is a solid, like all the cells in gray are solids. The ones that are highlighted in blue are liquids. This is at 0 degrees Celsius. The ones in red are all gases. And these we don't know yet because they just break apart. We don't know how they exist, which state they exist in. So I can change the temperature, then this also will change. So at 284 degrees Celsius, so these are all solids. You can see the number of liquids has increased. Sodium, potassium, they all melt at like 284 Celsius. And these are all gases. You can see that phosphorus has turned into a gas. Bromine, iodine also have become gases. These we don't know yet. Yeah, so this is to, like, it'll tell you, okay, at that temperature, what is the property that it shows. So both of these are interactive periodic tables. I'll send you guys the link to both. I would encourage you guys to play around. So one, you'll get familiar with the periodic table, and two, you also get to see like the trends and properties and all of that. You can like figure it out easily. Okay. Continuing, yeah. So you have S, P, D, and F. Okay. Make sense? Like, are you familiar with each of these blocks? What is where? Yes, no?
Kind of.
Kind of. Okay. So we'll just do like a couple of questions, like fun ones, just to get you guys familiar. What element do you guys like? Okay. Gold. What block will you find gold in? Which block?
Inert. Inert
Transition.
gases.
Which block, matlab? You need to tell me, yeah, SPDF.
P.
No.
Ma'am, D block, D.
D is absolutely right. So gold is AU. AU is right here. D block mein. Puneet, I can see why you've jumped to inert. Gold is inert, but you need to think of it on a more chemical way. So what makes inert elements inert is that they have fully filled, like they have octet configurations. Their valence shells are fully filled. You don't find that with gold. Like that's not the reason why it is inert. It's just not as reactive as the others. Like helium, neon, argon, krypton don't even react with aqua regia or anything at all. But gold does dissolve in a mixture of nitric acid and hydrochloric acid. It is capable of being oxidized, right? So silver does get tarnished. It's just at a much slower rate. That's why we consider them as, that's why we don't call them inert metals. We call them noble metals or unreactive metals. But these are all like absolutely perfectly inert. Only xenon makes, like it is known to make compounds with oxygen and fluorine, but that's it, nothing else. Okay. Sodium. Which block is sodium in?
Ma'am, what is the valency of xenon?
S.
S block.
S block is correct. Valency of xenon is group में है, fully filled shell है, तो
0.
क्या होगा?
Then how will it react with oxygen? Matlab, what will it share or give away?
Yeah, those are slightly unstable compounds, and the reason why xenon forms compound with oxygen is not because of xenon, It is more because of how reactive oxygen is. So specifically, oxygen and fluorine are the most electronegative elements. They are so powerful in pulling electrons towards themselves that like they attract the electrons around xenon so much that they end up forming a bond with it. So it's not that xenon is reactive, it's that these elements are so reactive that they end up forming a bond with xenon. Yeah. But they are known, like you will study more about them in grade 11 and 12. So yeah. Phosphorus is which block?
P.
P block
P
is
block.
yes.
P.
Yeah. Good. Fairly familiar. Non-metal है तो P block में पक्का रहेगा. Metal है तो you have to see is it like a reactive metal? तो group 1, group 2. Like valency अगर 1, 2 है तो group 1, group 2 में होगा. It's like a regular everyday use का metal तो D में रहेगा. And some metals like aluminium, just be careful, you can see it over here. Okay. So 18. So first step of classification is 4 groups you have, 4 blocks you have, and within those blocks again you have each of these vertical groups that you group them up in, and then you can like study them easily. Okay. Some groups are quite important because they like those elements react with a lot of other elements, are pretty reactive, pretty commonly found. So group 1 elements, these are called alkali metals. This you're familiar with. Alkali metals, we use it to, like we use this name for this set of metals, lithium, sodium, potassium, rubidium, cesium are also included in it. So the reason is that they form pretty strong bases that are soluble in water, which is called alkali, like acids and alkalis. So they form alkalis, that's why they're alkali metals. Group 2, this set of metals, magnesium, calcium, strontium, barium. So they are called alkaline earth metals. Yes. Because again, they are also alkaline, like they show basic nature, and you find these metals in the earth. Like calcium, you have a lot of minerals, you have limestone, you have fluorides and all of that. Magnesium, strontium, barium, you have barytes, baryites. So you find them in the earth's crust as rocks. So that's why you call them that. Noble gases, like, yeah, this is the group. This group, they're called halogens. So these 3 are the most common names you will come across, you know, when we are talking about reactions, properties. Oh, how does sodium react with halogens? You know, that sort of a context. Apart from that, group 16, you don't use them that frequently, but just for information, I'll give you guys the names. So this group, they're called chalcogens. And group 15, these guys are called nicogens, PNI. Okay. And group 18, though, you know, group 18 is noble gases or inert gases. Special names. Okay. So these are like the 5 common names. Out of this, alkali metals is pretty common. Alkaline earth also you should know. Halogens you should know. Noble inert gases you should know. So these 4, it's like in text you will find it pretty commonly. Chalcogens, nicogens, just know it for your information. It's not used so frequently. Just for like trivia type. Okay. Clear?
Yes, ma'am.
Yes.
Okay. Clear. So this is like the normal usual arrangement of elements. Now arrangement of elements, again, increasing order of atomic number, right? And we've seen atomic number basically directly relates to the electronic configuration. So that's where your similar physical chemical properties is also coming from. Okay. So you can find out the patterns yourself. For example, group 1 may, because you're already familiar with electronic configuration of lithium, sodium, potassium, can you tell me what is common between all these elements?
Valence electron.
Yes. What is the number of valence electrons in group 1?
1.
1.
Yes.
That's why they're called group 1, group 2.
Kind of, but don't get
Until group
confused with
7.
that pattern. Group, yeah. Not even till group 7, like here only it breaks down. Because यहाँ पे D block
4.
चालू हो जाता है ना. It's again, you'll have to get into that SPDF electronic configuration to make sense of it. But just for looking at the pattern, okay. So group 1 में there's 1 valence electron. Group 2 में how many valence electrons?
2.
2. Let's ignore D block because you'll need some more knowledge for that. Group 13 may how many valence electrons?
3.
3. Group 14?
4.
Group 15?
3.
Number of valence electrons. I'm not talking about valency.
Oh, not valency. Oh, then 5.
5. Group 16?
6 and 7.
7. And then 8 with the exception of helium. But yeah, let's call it octet or like completely filled valence shell. So that's the problem with modern periodic table. That's the only problem with modern periodic table. Position of hydrogen and position of helium. Like like, should I put helium over here or should I put over here? Hydrogen, should I keep it over here itself or should I keep it over here? So that's the doubt with these two elements. But that's also only because they have a single shell. Otherwise, the rest of the patterns, they follow beautifully. So, okay. So based on this, so that's like another thing with modern periodic table, because you have, like, you're familiar with the atomic number 20 tak, it is very, very easy to figure out the electronic configuration also. Like, for example, if I want to know the electronic configuration of silicon, which is over here, all I have to do is count how many elements are coming before it in every period. So before I reach silicon, I need to go through first period, which has 2 elements. Then I have to go through second period, which has 1, 2, 3, 4, 5, 6, 7, 8 elements. Then when I go to third period, to reach silicon, I have to go through 1, 2, 3, 4 elements. So electronic configuration 284. So this way you can figure out the electronic configuration for any element. So calcium also exactly like that. So 2, then isme 8, this may 8, and this may 2. So Mansi, I'm just like, based on, because they all follow the same pattern, you can figure out the electronic configuration of any element just by looking at the periodic table. So how do you do that? You just have to count how many elements are coming before it. So I'll do it again.
For all periods, can you do?
Huh?
Can you count the elements for all the periods?
Technically, yes. Like that's how, like even when you go a level higher, if you were to look at subshells and orbitals and all also, that's the same pattern that you use. But yeah, for now, since we are just looking at the total number of electrons, we'll stick to that. So for example, if I were to find the electronic configuration for potassium, which is over here. So K ka electronic configuration will be, start from 1. First period mein how many elements do we have?
Two elements.
Then second period mein how many elements total do I need to go through? 8 plus 1, 2, 3, 4, 5, 6, 7, 8. फिर पोटेशियम इधर है ना, उसके पहले थर्ड पीरियड में how many elements do I need to go through? 8. Then fourth period में how many elements should I count to get to potassium?
1.
1. So this is the electronic configuration for potassium, 2881.
Can you show it for zinc?
Zinc, definitely. Zinc will be 2, 8. So zinc, because it's a D block element, so there's a trick to it. Like pehle 2 electrons go into the fourth shell and then they start filling up the third shell again. Like remember, based on 2n square property, third shell can take 18 electrons. So 8 ke baad remaining 10 electrons get filled after going through the 2 electrons over here. Yeah, Divya, what's up?
Because I was actually disconnected 5 minutes ago. Where are we now?
No, I was just discussing electronic configuration, like how to use the periodic table to figure out the electronic configuration. So you can do
No,
that.
I heard group 7, groups, periods. I heard all that.
Yeah. Okay. So zinc ke liye, so 2, 8, then 8 electrons get filled in this, like 3s2, 3p6. Uske baad 2 electrons in the fourth shell. And then like this is the 3d orbital that gets filled here. So 8 plus and 10 electrons get filled over here this way. So that's why like once you start like step into D block category, no, it gets a little complicated. Uske liye you need to have some extra knowledge of the structure of atom, which you guys didn't study abhi. So let's not worry about that right now. Okay. Okay.
But D block is out of portion.
No, out of portion matlab you just need to know D block exists or usme kis tarah ke elements hote hain. Just know that,
We don't have to study like S and P block here.
Like you don't have them in detail, but you need to know that SPDF blocks hote periodic table mein, and at least the rough placement. Group 1, 2 is S, last 6 are P, D is beech mein, and F is lanthanides and actinides. That much you need to know. Like what are they, you need to know. Anomalous position, maximum number of electrons you can figure out. Let's get into trends. Okay. Can you tell me what all properties do you have for trends? Like I know metallic nature hoga.
Number of shells, the valence electron.
Number of valence electrons, ठीक है. We discussed that. Do you have ionization energy?
In textbook, it is not there. Just in chapter notes, it has been given. Ionization and one more.
Ionization energy, electron affinity.
Ma'am,
Atomic
the
radius.
atomic size. Yeah.
Atomic size is quite important. Very good. Yes, atomic size discuss karna padega. This I know we'll discuss. This we'll know. This I can discuss. फिर reactivity भी थोड़ा discuss कर सकते हैं. But tell me if it's there in your school, I'll go in detail. Otherwise, I'll touch on it based on how much time we have. So tell me ionization energy, electron affinity, and electronegativity. So electronegativity, electropositivity. So tell me if you guys have these four. I'll discuss this. Otherwise, I'll give this less priority. Let's focus on what you
Ma'am,
syllabus. Yeah, Divya?
ma'am, we had like valence electrons,
Hmm.
atomic size, and metallic and non-metallic character, like main, which had the mean.
Okay.
Yeah, not done that. Other four.
Okay. So these four, you haven't touched on it in school.
Not in a textbook. I've not read.
Textbook, your school teacher also hasn't done this or
Yeah,
have
not done.
not
No,
done.
no,
At the
not.
most, I think they are electron affinity with the metallic nature itself.
Yeah. No, electronegativity, electropositivity directly connects to your metallic nature. These two are like energy values. They are also kind of all related, but different physical quantities. That's why, before we get too much in depth, I need to understand if
Ma'am, there are only three only main.
ठीक है. So we'll stick to those three, and then if you guys want, if you're interested, either this class or after your exam, sometimes we'll take this up. Okay. Valence electrons we already discussed. Number of valence electrons keeps increasing, at least group 1, 2, and then 13 to 18. Next, metallic nature. So observe, where do you find most of the metals in the periodic table? Like left side, right side, top, bottom?
Left
Transition metal.
left side, bottom.
Yes. So let me highlight the metals. So in general, all the metals you see are on the left side, and then non-metals you see are on the extreme right side. Okay. So based on this, let's take it up slightly more granular. So in a single group, okay, before we get to group and period, how do you differentiate metals and non-metals?
Metals give out
They form
electrons.
positive ions and non-metals form negative ions.
Excellent answer. Very good, both of you. So metals have a tendency to release electrons. Non-metals have a tendency to gain electrons. Yeah, like release electrons, matlab, that's how they form positive ions, and these forms negative ions, anions. Okay, keep this in mind. Now let's take group mein. Within a group, top to bottom. Okay, so let's compare lithium. Like let's compare lithium versus sodium versus potassium. Lithium का atomic like electronic configuration क्या है?
2,1.
2 1.
Sodium
281.
8,1.
very nice. Potassium
2881.
8,8,1.
2 8 8 1.
very good. So like as you go from top to bottom, like what is happening between lithium and sodium and then sodium and potassium? Like हर एक में difference क्या? Like what do you observe? What's happening over here?
88 electrons or
One
a
more
shell is
shell.
added.
Where yes, so lithium has only 2 shells, sodium has a 3rd shell, and potassium has 4th shell. Okay. So lithium basically looks like this, 1 and then 2. Then sodium has 1, 2, and 3. And potassium is like 1 more, it's increasing. And there's no space here, but imagine like 4 shells there. Now, if you consider the tendency to remove an electron, so between lithium, potassium, and sodium, in which case will you be able to take an electron easily?
All of them.
Potassium.
All of them, yes, but within these three,
Potassium.
Puneet is saying potassium.
Because in the valence electron, the effect will be less because as the distance is increased towards the nucleus. Because nucleus
Correct.
charge.
Yes, absolutely right. Okay, see, how are the electrons existing in these shells? Nucleus may you have protons, and protons ka what charge do protons have?
Positive.
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 Yes. So positive charge or negative charge of electron ke beech mein what sort of force do you find?
Attraction.
Attractive forces. Okay, so that's what is holding the electrons within the shell. So agar electron hai shell mein, and if I want to take it out, I need to get over this attractive force. So if you compare lithium, sodium, and potassium, तीनों के केस में, do you think the force of attraction will be equal or will it change?
Change. It will decrease from top to bottom.
Nikki, Mansi, Dhruv, what do you guys say?
Yes, ma'am. It will decrease.
Like you guys studied gravitation also, no? Any kind of attractive force, if you increase the distance between them, the force is going to reduce. Yeah. So because of that, lithium is going to be really like generally compared to like oxygen, fluorine, and all, it's easy. But within these 3 elements, between these 3 elements, lithium is going to be difficult. Then it gets easier with sodium, because force is reduced here. And it gets even more easier in potassium because the force is even more reduced here. Okay. So based on this property, what can you say about the metallic nature as you go from top to bottom in a group? Like
Increases.
correct. So metallic nature matlab how easily can an element release electron? So because of this increased size, increased distance, it gets easier and easier to remove an electron as you go from top to bottom in a group, which means that metallic nature increases in a group, increases when you go from top to bottom in a group. And what can you say about metallic nature going from left to right?
Decrease.
Left to right? you can see that it decreases. Like left side pe sare metals hai, right side pe sare non-metals hai, and that's again related to the electronic, like partly electronic configuration and ionic, the atomic size also. So metallic nature decreases left to right in a period. ठीक है? Divya sent something. Yeah, Divya, like the image that you sent, that's a good like summary of it, but you also need to know the reason why it's happening. A certain reason aa sakta hai, and in general, like, you know, the if you understand the details, आसानी से आ जाएगा.
Ma'am,
Yeah, Elena.
ma'am, but if we like see in the example which you gave of lithium, sodium, and potassium, the number of protons are also increasing, right? So won't the control of the proton increase on the electrons?
That's a very good question, Alina. Yeah. So the number of like positive charge overall is increasing between lithium, sodium, and potassium, but the magnitude of force, like the distance has more of an effect on the magnitude of force than the number of electrons, because one, number of protons is increasing, but you have the number of electrons also increasing, right? Like यहाँ पे 2 electrons है, यहाँ पे there are 8 electrons, like 2 8 1 बीच में these electrons also play a role. So in terms of magnitude of the charge, the effect of the increasing number of protons is not as much as what the effect of the distance on this lone electron is. Okay.
Okay,
So it's
ma'am.
directly proportional to charges, inversely proportional to r square, just like with gravitational force. Force between two charges also follows the same pattern. So this has more of an effect. So if the distance is increasing, the force reduces by a lot. Okay. So when you guys note this down in your notes, just mention the property, metallic nature. Compulsorily put like group mein what is the trend, like top to bottom increasing or decreasing, and then period mein left to right, is it increasing or decreasing? Just mention this, and then iske niche put the reason. You know, like group mein it's increasing, or like beside this only on the right side you can mention the reason due to increasing size, that way. Okay, so that's metallic nature. Then atomic size. What do you mean by atomic size?
Distance between the nucleus and the valence shell.
There you go. It's literally the radius of the atom. Sometimes you also see it mentioned as atomic radius. Basically, it's the size or radius of the atom. Nucleus hai, and then you have electronic shells. So the distance between the nucleus to the valence shell, like measure it all the way to the edge. Okay. Now finding the trend of atomic size is pretty easy for a group. In a group, as you go top to bottom,
The radius increases.
yes, increases. Reason?
More shells are added.
Absolutely. It's very, very direct. You can directly see that lithium may there's only 2 shells, sodium may there's 3 shells, potassium may there's 4 shells. Rubidium may, can anyone guess how many shells are there in rubidium?
5.
5 is absolutely right. It's 2, 8, 18, and then 1.
The period number depicts the number of shells.
How
Yes.
do we write 18? We write 8 as the highest number, right?
18, 8, 1, something like that. Yeah. Your third shell is completely filled, but the fourth is not.
Miss, how did you write 18 there?
That is the electronic configuration. Don't worry about it. But this one has 5 shells. Yeah. So it has like the third shell completely filled. For fourth shell, like S and P block are filled, but D block is not filled. So यहाँ पे बस there's only 8 of them, and then 1 आएगा ऐसे. No worry, but yeah. So as you go from top to bottom, there is an extra shell added, and hence atomic size increases. You can note this down as trivia, like another pattern, interesting pattern you can see that the period number is equal to the number of shells that the atom has. So all the elements in third period will have 3 shells. All the elements in fifth period will have 5 shells.
Helium has 18 shells.
18 कैसे? The period number, like this is.
Okay, no, 1 to 7.
Yes.
Okay.
Horizontal row. Like the row number is directly equal to the number of shells that that atom has. Yeah. So group is pretty easy to understand. As you go each step, like one step bottom, the number of shells increases. Same thing with halogens also. Fluorine is 27, chlorine is 287. This is 28. Yeah, basically it increases. Again, 28, 18, 7, whatever. Next, now coming to horizontal rows, periods. So as you go from left to right, so atomic number, atomic size, that is, does it increase? Does it decrease? Or does it remain the same?
Remain the same.
Decrease.
Okay, 2 people, 2 answers. Anirban, Elena, what do you guys think?
Decrease.
Please. Elena?
It'll decrease, I think.
Okay. Dhruv, Mansi, Divya, what about you guys? Mansi says decrease. Divya is also saying decrease.
I guess decrease.
Okay, most of you are saying decrease. But what is the reason why? Like I said, same number of shells now. If I compare sodium, magnesium, aluminium, they all have the same number of shells. 281, 282, 283. So reduction कहाँ से आ रहा है?
Cell will be the same, but there will be an increase in the electrons and the protons, due to which the attraction force will increase, causing it to come near the nucleus.
Yes, that's where you need to get into. Okay, so for this, I'll use the
But
whiteboard.
ma'am, in case of size, the radius we mark enter to the shell, right? So number of electrons won't matter. The shell distance will remain the same.
But those electrons are held by the positively charged nucleus, na? So that nucleus is having like an attractive force on those electrons. So that ends up causing an effect. Now, like that's what we'll get into. I'll use the whiteboard for this. So let's take the second period, okay, because that is easy to demonstrate. Second period, if anyone has periodic table in front of them, what are the elements that are there in the second period?
Beryllium, magnesium.
Shuru se. Second period, not second group.
Oh, second period.
Don't be confused group period में, हाँ. Lithium,
lithium, beryllium,
hmm,
boron, carbon,
hmm,
nitrogen,
hmm.
oxygen, fluorine, and argon.
Fluorine and
Argon.
argon or neon?
Oh, wait, no.
Now it is
Neon.
Neon.
Increasing atomic numbers. अगर यहाँ पे 9 है तो यहाँ पे 10 आएगा. Okay. Okay. So let's see electronic configuration. Lithium is 2 1. This is 2 2. This is 2 3. 2 4. 2 5. 2 6. 2 7. 2 8. Let's look at each atom because we're looking at atomic size. So lithium has 3 protons. So nucleus में +3 charge है, and then 2 shells. So beryllium also has 2 shells. Boron also has 2 shells. What I'm drawing is not to scale, okay? Like, don't base your radius on this. ठीक है. Lithium has बीच में +3 and then end में 1 electron. Beryllium has +4 in the center and यहाँ पे -2. This has +5 and 3 electrons. This has +6 and then 4 electrons. This has +7 in the center and 5 electrons. This has +8 in the center and 6 electrons. यहाँ पे there's 7 electrons and +9 in the center and 8 electrons. Okay, so imagine the distance between nucleus to single electron, nucleus to say 4 electrons is the same, but +3 is exerting force over the valence shell. Now all the electrons exist at the same distance from the nucleus, okay, whether it's 1 electron, 2 electrons, whatever it may be. And electrons kind of exist in a cloud, like they are not single particle that way. Now as you go from left to right, what is happening to the nuclear force, like the power of attraction of the nucleus?
It increases.
Yeah, so from left to right, the attraction of nucleus is increasing because the number of protons is increasing. So these protons are all exerting force at the same distance over these set of electrons, whatever set of electrons are there over here. So again, remember, force of attraction depends on 2 things. One, it depends on the quantity of charge, the magnitude of charge, and it is inversely proportional to the distance. The distance remains the same because all of them are in the second shell, but the magnitude of force, like one of the charges keeps increasing here. Like protons are also increasing, number of electrons are also increasing here. So what do you think will happen to the attraction as we go from lithium to fluorine? Nikki?
Ma'am did not understand the question.
Okay. See, force of attraction, it depends on how much charge is there, and it also depends on the distance between the charges, like the positive charge and the negative charge. Abhi, in all of these atoms, the distance between the charges is the same, right? Like second shell hi hai sabka. But the force that is being exerted from the nucleus to the valence shell, the number
Is increasing.
like the charge keeps increasing, which means the total force exerted by lithium ka nucleus will be less than whatever oxygen ka nucleus is exerting. And then fluorine ka is like even more. So if the force keeps increasing, what will happen to the outermost electrons? Will they be in the same place, or will they be like, will they come slightly closer? Like, what do you think is the consequence of that?
Closer.
They'll keep coming slightly closer. Divya, are you able to visualize? Like, I getting understanding? Anirban?
Yes.
So if they keep coming closer, what do you think will happen to the atomic radius?
It is the same, right, for all of them.
You just said they're coming closer, right? So if they're coming closer, so what happened to the radius? Like if I compare
Decreasing.
lithium ka radius with fluorine ka radius, it ends up decreasing. Yeah. So the periodic trend, as you go from top to bottom in a group, atomic radius increases. But as you go from left to right in a period, the atomic size decreases. Obviously, it's not like a really big decrease. It's not as much as what this increases, but it's still like a significant decrease. And the reason why it is decreasing is because as you go from left to right, the atomic number increases, which means that the number of protons is increasing by 1 in each step, while the number of shells remain the same. So more charge applied at the same distance means more force of attraction over those electrons. So zyada force if they're like attracting, itna hona tha, it kind of comes a little closer. So the consequence is that the atomic radius decreases slightly. Okay. Like, guys got it? Makes sense? Yeah, okay. Nikki, what do you say? Like, agreed or?
Yes, ma'am, I'm getting it now.
Okay.
Agreed.
ठीक है. Electron affinity, let's just ignore. So put it in simple words. Yeah, atomic radius decreases left to right because increase in nuclear charge, which tends to pull the electrons closer to the nucleus, and it reduces the size of the atom. Metallic, non-metallic properties we have discussed. So metallic left side.
Ma'am,
Hmm?
miss, if the number of electrons and the protons increase, then why doesn't it occur the same in metallic nature? Due to the addition of shell, it does not increase or decrease.
See, metallic nature, non-metallic nature again relates to how easily the electron can be released, right? See, left to right, if the force of attraction is increasing. So fluorine holds on to its electrons with more force than lithium does. So in which case will it be easy to remove an electron?
Lithium.
Lithium, right? So metallic nature decreases from left to right, increases from top to bottom. It's the same with like metallic nature is same as atomic radius. So size increase हो रहा है मतलब metallic nature भी increase होगा. Size reduce हो रहा है मतलब metallic nature भी reduce होगा. Okay. Does that
Okay,
answer
ma'am.
your question? Okay.
Yeah, ma'am.
हाँ. Metallic non-metallic properties फिर valency भी discuss कर लिया like based on the number of valence electrons. All of these we'll deal with this later. Fancy nuclear charge, atomic radius, metallic character. These three you can just like worry about it. Okay. So that is the main like bits of the chapter. So it's all about, just looking at the elements, playing around with them, observing them, what is happening top to bottom, what is happening in like different blocks and all of that. Do you guys think you can answer questions on your own, or like it's already 5:10? So if you want, we can discuss questions for like 15-20 minutes, or I can assign homework for you guys and you can do it on your own. What will you prefer?
Homework, ma'am.
Ma'am would prefer to do it in the class, but not right now.
Okay. Attempt it. I will check and
Ma'am, you can give few important questions
Yeah.
at home, like
yeah, that's what I
4
was
to
thinking.
5.
Yeah, 4 to 5 तो बहुत कम है. I will check and I'll give you guys the list of questions that make sense, that are application based thoda sa. Attempt it on your own. If you're stuck somewhere, put it on WhatsApp. Chota sa doubt
Ma'am,
hai.
because we've never really solved questions of this chapter. We've only done the theory part, like school as well.
Acha.
So it will be better if we start it in the class, and then if it's going smoothly, then later on you can just give the homework and continue with the next chapter.